document or a PDF file, whichever one you want to open. And this document says how to calculate confidence intervals. Okay, so I'm going to open that one first. Okay, so you guys online should be able to see that also. Okay, good. All right, so guys, I just opened up the document. Hopefully you can see behind me. And I know you got a lot of theory just now in the lecture, but from this point on, we're going to deal with calculating confidence intervals from like a practical point of view. Okay, we're going to actually work on doing a number of them. Okay, so let's take a look just very quickly on how we verbally, what's the procedure that we're going to use to calculate a confidence interval. First thing is that we're dealing with a population that we think is roughly normal. Doesn't have to be perfectly normal. Remember, the central limit theorem says that even if the population isn't perfectly normal, that if we take repeated samples from that population, the distribution of those sample means is more normal than the original population was. Okay, so that allows us a lot of latitude in working with populations that may not be perfectly normally distributed. So we're dealing with a continuous variable that, whenever we're working with means and standard deviation, we're dealing with a numerical or a continuous variable, not nominal variable, not an ordinal variable. And we're usually dealing with a random sample of independent events. In other words, we're randomly going to sample an entire population. So we get a pretty good cross-section of what the population is like. We don't want to bias that sample. So we're dealing with a random sample. We're going to take a random sample. We're going to find an average for that random sample. Sample size might be small, 10 people. Sample size might be large, 100. It might be extremely large, thousands of people. Okay, but in any case, we're going to take a sample and we're going to get the mean. Now, the mean of the sample, I'm going to term X bar, X with a little bar over the top of it. If I'm talking about the population mean, I'd be calling it mu instead. Greek letter mu means the population mean. A X bar, X with a bar on top, or X, sometimes I'll just write it out X bar because it's easy for me to type. X bar means the mean of the sample that you took from that population. One is a parameter, that's the mean, and one is a statistic, that's the mean of the sample. Okay, so the other thing we're going to be interested in besides the mean is going to be the variability in the population and in the sample. Okay, when we calculate the variability in the, or standard deviation in the population, we give it the name sigma, right? The Greek lowercase sigma. And that represents the variability. Remember how we calculated that in the beginning from samples. But if we did it for the entire population, we call it sigma. If we're just calculating it for the sample, we call it Srsd, standard deviation. Okay, again, plain letter, not Greek letters. And that's a statistic. Now, we're interested in the behavior of samples, sample means. So we're going to go one step beyond that standard deviation of the population or even of the sample, and we're going to calculate something that's the standard deviation of repeated samples of the same size. In other words, if the sample size is 25, we're going to get a mean. Do it again, we get another mean. Do it again, we get another mean. Now, all of those means, we're going to look at the new distribution of those. And that's going to form a normal distribution. And the middle of that distribution is going to approximate the mean of the population. But the standard deviation, the spread of those numbers, the standard deviation of those numbers is going to be narrower. It's going to be a smaller number than the standard deviation of the entire population. Just simply because we're averaging them in, they're going to be all closer to the mean. Yes?
Which is the parameter and which is the statistic?
Parameter is when you're dealing with the population, mu and sigma. Statistic is when you're dealing with a sample, which is X bar and SD or S, whatever way you want to term it. And it should be easy to remember because we're in this class, we're never going to deal with the population because you never know what the population is. This is called statistics. So we're always dealing with a statistic. We're not dealing with the parameters. Okay, so So at any rate, so we define a new standard deviation for that sample distribution, whether it's sample size 25 or sample size 100 or whatever its sample size is. We're going to define a new variability, a new standard deviation for those repeated sample results, sample means. Okay, we're going to call that the standard error. We're just going to it's calculated the same way. We're just going to give it a new name so that we can so it's easy for us to distinguish between the population standard deviation and the standard deviation of these repeated samples. So standard error is going to be smaller than the standard deviation of the population. In fact, we did a little experiment last week, and we determined that it's going to be standard deviation of the population divided by the square root of the sample size. So if the sample size is 100, then the standard error is going to be 1/10 of the size of the standard deviation, because the square root of 100 is 10. Make sense? Okay, so that's how we're going to calculate that. Now, in a lot of the examples we're going to start with now, I'm going to tell you what the population standard deviation is. In general, in real life, are we going to know what the population standard deviation is? Probably not, right? It's probably going to be pretty unusual for us to know that. So how are we going to figure out what the population standard deviation is? Well, we only got one way to find that out. We can estimate it from the sample that we took from that population. There's a problem with that. We have a certain amount of error that we're generating because we're calculating, we're predicting what the mean is based on the sample. And then we're also going to guess at what the standard deviation is based on the sample. That's not as good. That gives us more uncertainty than just than knowing the standard deviation of the population. If we knew the standard deviation of the population, that eliminates one layer of uncertainty. But if we have to estimate it from the sample population, well, that's a little bit more uncertainty we have to deal with. So the way we're going to deal with that is that if it's a very large sample, we're going to say to ourselves, hey, it's reasonable to expect that the standard deviation of our sample is going to be a pretty good approximator of the population standard deviation, right? But if it's a small sample, right, then it's not very reliable. We're not going to deal with that this week. We're going to deal with small samples next week. All we're going to deal with this week is when we know the standard deviation of the population, no error involved, and when the sample size is very large and we think it's a pretty good approximator of the population. I'm sorry, was there a question?
Yeah, I was just
Okay.
gonna say that.
Okay, so what do you think what do you think would be a good number for us to pick as a large sample?
50?
50 sounds pretty good, right? How about 100 or 1,000? In fact, for reasons that will be a little bit clearer next week, believe it or not, we're going to consider anything over 30 as a big sample. Okay, it doesn't sound like a very big sample, does it? But when we look at the Z table and what we're going to work with, the T table particularly next week, we're going to see that when we start to get to a number like 30, then we get a pretty good guess at what the standard deviation of the population is. We'll see that in those tables next week. We'll have a pretty good feel for that. This week, we're not going to worry about that. We're only going to deal with large samples, bigger than 30, probably quite a bit bigger than 30, just so that we can deal with it that way, or situations where we know the population standard deviation. So how are we going to calculate our confidence interval? Well, our confidence interval is going to be a range of numbers, a lower limit and an upper limit, within which we're 90 or 95 or 99% certain that the true population mean falls. And the way we're going to determine that is, I'm going to take a look at this outline of a normal distribution that shows the empirical formula, or the ranges for the empirical theory here. So our experience tells us that if I have a normal distribution, right, and now remember these standard deviations, if I'm dealing with distribution of sample means, these sigmas are really standard errors, right? So rather than standard deviations. I have a reasonable expectation that 95, if I take a sample from a population, that 95% of the time I will get a result that's within 2 standard deviations below, 2 standard errors below the mean and 2 standard errors above the mean. What area is that represent? What percentage of the outcomes or means that does that represent of that sample size? 95%. So we're 95% sure that within that range that we would get the actuals that we would get a sample result from that population that is within that distance of the real mean, the real population mean, which we don't know, which we often will never know, right? That 95% is important to us, right? Now, if I wanted to go to 99%, I'd have to go to almost 3 standard deviations. Actually, not really 3 standard deviations, but pretty close to 3 standard deviations, 2.5 or 3 standard deviations away from the population mean to be sure that 99% of the time that our sample mean result is going to be within that range of numbers. Okay. We're going to use this a bit differently than worrying about how far our sample mean is going to be from the actual population mean, because we really don't know the population mean. We wouldn't be able to check it, really, would we? So the way we're going to use this instead is we're going to say to ourselves that the range of numbers that we're going to represent our range of confidence is going to be equal to, is going to be equal to the mean that we calculate from the sample that we take. Remember, now we're only taking one sample. It's going to be the mean of our sample result. Let me make that bigger. Our range of number, our lower confidence limit to our upper confidence limit is going to be equal to the mean plus or minus the standard deviation of the square root n. That's the standard error. I could just as easily just write SE for standard error in there, right? 1.96 times the standard error. In other words, actually, if I use the empirical formula, that would be 2 times the standard error. So what is that? This is 2 standard errors below the mean and 2 standard errors above the mean. Just what we outlined in this diagram here, right? So what I'm saying is, if I calculate a mean of 100 for a certain population with a standard error of 10, I would expect that I would call my confidence interval 100 plus or minus 2 times my standard error. 2 times 10 is 20. Plus or minus that 2 times 10, that 20. So I would call my confidence interval 80 to 120. So my confidence interval would be 80 to 120. So although the sample mean I predicted is going to be around 100, I don't really know how accurate that is, but based on what I understand about these population standard deviation, my calculation for the standard error, I can say with 95% certainty that the true population mean is between 80 and 120. Yes?
The 1.96 from the Z table?
Yeah, where'd that come from? Anybody remember? I just used the empirical formula to say 2 times. Why did I have 1.96 written in there? Because the empirical formula, empirical means like based on an estimate or based on experience, right? So based on experience or based on an estimate, it's 2 standard deviations for 95%. If I look at my Z table, is it really 95%?
How come it's not 2.5?
2.5?
For the empirical. Because then that's for 95%, then you have 2.5 on either side.
It is 2.5 on either side, right? In fact, if you look here, see if I go here, this is 2.1 and 0.1. If I add them together, it's close to 2.5%. If I add these two together, it's close to 2.5%. They actually, they're not that precise in this drawing. In other words, these ranges aren't as precise as these numbers are. So when we say 95% confidence, we mean that 95% of the outcome, 95% of the area of this distribution is between 2 standard deviations or 2 standard errors below and 2 standard errors above. Okay, that leaves 2.5% at one end and 2.5% at the other end. That's called two-tailed. Later on, that's going to come up. If I said to you, I want to be 90% confident, right? What percentage of this distribution would be below that limit and above that other limit at the top? Below the lower limit, above the other? Well, there's only 10% left, right? So that would mean 5% is below in the lower tail and 5% is above in the higher tail. Okay, how about 99% confidence interval? Then 0.5% would be left in the tail at the bottom, and 0.5% of the possible outcomes would be left in the upper tail. Okay? But why 1.96? Well, let's open up that table. Okay, and I'm going to take a look at the air at 1.96. Now keep in mind that the z-scores that are on this table, the negative z-scores, represent the area to the left of that z-score. So 1.90123456 represents exactly 2.5%. Right? So that z-score of 1.96 standard deviations or standard errors leaves 2.5% on this end of the distribution. It leaves exactly the same amount on the other end of the distribution plus 1.96 because it's symmetrical. Normal distribution is symmetrical. That's why we use 1.96 instead of 2. It's more accurate than using 2. Could you use 2 to get a rough idea? Sure. But it's not as accurate as using that value 1.96. Okay. Now I'm going to ignore the fact that I've already broached the subject of 99%, 90%. Let's forget I even brought that up for now. Okay. So we'll get to that. You're covering your mouth like this is horrible. Right? It's not that bad yet, right? We still got a long way to go. Okay. So it's simple enough. We're going to calculate the mean for the sample plus or minus 1.96 for what confidence interval? The 95% confidence interval. 1.96 times the standard error, which is calculated by standard deviation of the population divided by the square root of the sample size. The bigger the sample size is, right? The smaller the standard error is. The smaller is 1.96 times the standard error. The smaller is the difference that you're adding and subtracting to x, which makes the width narrower. The bigger the sample size, the narrower your 95% confidence interval can be. The smaller the sample size, the less confident you are, so the wider it's going to be when we do the calculation. And this is all going to tie in and make sense in a few moments. We also can do a similar calculation to do it for proportions, but I'm going to hold off on that for now. So I'm going to open up the document that has those exercises that I was talking about, and we'll give this an actual try now. It's a Word document or a PDF file, either one, that's on Blackboard right now. It's called, let's see, I have to go back here and open it. Called PH750 3/16/15 Lab Session 6. Okay, it should be on there, right? You guys can get to it. Okay, let's take a look at this first possible problem that we might have. The mean of a population is known to be 160. The standard deviation of population is known to be 20. What would be the probability that a single observation, we're kind of prefacing what we're about to do, looking at just the population itself. What would be the probability that a single observation selected at random from the population would have a value of less than 154? Well, we're just working with the population, right? You guys remember how we would calculate the z-score there for that individual that's 154? It'd be 154 minus 160, which would be 6, divided by 20, right? So the z-score would be 6 over 20, which is how much? Let me get my notebook here.
It would be like negative 6 over 20 if you look at the negative side.
Yeah, it's on the negative side. So, okay, oops, wrong direction. Here we go. Good. Okay, let me make sure these guys online can hear me. And okay, everything's working. Oh, good. I see we got a little chatter in the background going on there. Good. Okay. Okay, so what did I say the population, the mean was? 160, right? Right, and that's mu. and standard deviation was equal to 20. And I'm examining the value for, let's see, one standard deviation would be like 140 over here. And I was looking for 154. So 154 would be around here somewhere, right? Because I know that one standard deviation would be over here, so I know it must be closer to the mean than that. So the z-score here is going to be equal to 154 minus 160 over 20 is going to be equal to minus 6 over 20, which is equal to, well, what is that, 0.15?
0.3?
I'm sorry, 0.30. Okay, negative 0.30. And what did I ask? What was the question there? What's the probability a single observation would have a value of less than 154? So here's all the possibilities that you would pick somebody out at random that would be less than 154. So I'm going to use my t-table, my z-table. Okay, find it. And look up that z-score, minus 0.03. And that's 38.21 is the area to the left of that. 38.21% or 0.3821. 3821. So the probability that you would pick an individual that has a, whatever this is, blood pressure, blood sugar, whatever it is, less than 154 is 38.2% or 0.382. Okay, so let's take a look at the next question. What's the probability a single observation would have value greater than 166? 166 is going to be about up here somewhere. Here's 166. And this z-score is going to be 166 minus 160 over 20 is going to be plus 0.30. Well, we know that this is symmetrical, right? So if we're z-score of negative 0.3 and this is 38.21, then this area is also 38.21% or 0.3821. Okay, in terms of a probability. So this is the area that's greater than that. Okay, so now, and what's the last question that we have here? It's the probability a single observation has a value between those two. Well, it's going to be this area in here. Right, and what's that area going to be? Well, it's going to be 0.38 plus 0.38, okay, which is going to be 0.76, right, roughly, 0.765. And we're going to subtract that from 1 to find what area is left in here, which is about, I'm going to say 0.23 for argument's sakes. Okay, so the probability of picking out someone that's between these two values is 23%. So that's just an exercise in working with the population. Now we're going to move on and we're going to work with samples. Okay, a random sample of size, did I left the size out there? Okay, random sample size n has a mean of 150. Assume the population is normally distributed. Doesn't have to be perfectly normally distributed, but we got that little extra. It has a standard deviation, the population. Sigma is 130. That's important. I know the population standard deviation. Calculate the standard error for sample size equal 100. So what's the standard error here?
Sigma over the square root of n.
Yeah, sigma over the square root of n. Let's get a fresh piece of paper. So let's see. Okay, I didn't mention a mean yet. Oh, I did mention a mean. 150 means 150, except this time we're looking at the sample distribution. This is the distribution of all the samples that we would take of size 100 from this population. So my standard deviation for all of those repeated samples of size 100, that would be equal to sigma over the square root of n. We know sigma to be 30, and we know the sample size to be 100, square root of 100. So that's going to be equal to 3. Standard error is going to be equal to 3. Okay, compute a 95% confidence interval for the mean of the population. Okay, 95% confidence. Well, did I say what the result of the sample was? Random sample. Oh, random sample has a result of, we don't know what the population mean is, right? I jumped the gun on that. We don't know. We know that the sample has a mean of 150. So how do we calculate our confidence interval? X bar plus or minus 2 standard deviations below and 2 above. I'll be a little bit more accurate and call it 1.96 times the standard error. Okay, and that's going to be X bars. So X bar, the sample result was 150 plus or minus 1.96 times 3. Okay, so what does that come out to? 150 plus or minus, and I'll calculate this. Okay, 3 times 1.96 is equal to 5.88. So this part of the equation is equal to 5.88. And I'm going to be adding 5.88 to the 150. And I'm going to predict that my true population mean is 150 minus 5.18 to 150 plus 5.88. What do you think? What do you think would be a good name for this number that I'm adding and subtracting from what I think the actual mean is likely to be? Bingo, margin of error. Great. We're going to call that the margin of error. Okay, good. This is the standard error, and we're adding 1.96 times 1.96 times that, and that's going to be our margin of error. We're going to say from this to this number is our confidence interval. Okay, so what does it come out to be? Well, the high end is, I know, is going to be pretty easy, 155.88, and the low end is going to be 144.12. I got that right? Okay, good. I can still do that. So our confidence interval is 144.12 to 155.88. Are we certain that our population mean is going to be between those two? No, we're not. But we do know what level of certainty we have, right? How reliable this is. We are 95% certain that the true population mean is between these two numbers. We may never know what the population mean really is, but at least now we have an idea of a likely range for the population, and we can quantify what our level of certainty or what our level of doubt is, right? In other words, there's 5% chance that it's not within this range also. Okay, so let's take a look at what else we can do with this. Compute a 99% confidence interval for the mean of the population. 99%. Well, what do you think we might do now for 99%? X bar plus or minus. The standard error is the standard error. That's not going to change. But how far out on the normal distribution I have to be of these sample means is going to change for 99%. 99%, this has to be 0.5%, right? Or 0.005, this area. And this area has to be 0.005 because the area between has to be 99%. Okay, what's the z-score for this value that gives me an error in the tail of 0.005? Let's look it up. Let's not take it for granted. Let's go ahead and look it up. Let's see, Srsd. Okay, so I'm going to do the same thing I did before. 0.005, the area that represents in that tail 0.005. I'm looking for the area inside this table. 0.006, 0.007, here we go, 0.005. I'm sorry, not 0.0005, 0.005. 0.005 looks like right about here. 0.00. What's that?
0.04, that column.
0.04. Where am I? 2 point. I'm going to go straight to it. Here we go. I'm going to go right over here. 2.2. Okay. 0.258. Okay. Now, why would I? Now I dodged around a little bit here, but I could have gone straight to it because we're going to get very used to the fact that the number we're going to use for the 95% confidence interval is 1.96. The number we're going to use for the 99% confidence interval is going to be a z-score of 2.58. That's going to be the closest number. You know, you can interpolate if you want to get a little bit more accurate, but 2.58 is going to be fine for our purposes. While we're here, what number are we going to use for a 90% confidence interval? What would be the size of the tail on either side for 90% confidence? Each tail would have 5%. So we got to find the area that would represent 5%. Okay, 0.04, 0.05, let's see. How about right here? 1.6, what is that? 4. So we're going to use 1.64 for a 90% confidence interval. Okay. Which one is going to represent the widest interval of those numbers? 1.96, 2.58, 1.64. Which one's going to give us the widest interval? 99% confidence interval is going to give us the widest interval because that's the biggest number we're going to multiply to get our margin of error. Does that make sense? The wider the interval is, the more certain you are that you're going to capture the mean between those two numbers. The narrower the interval is, the less certain you are you're going to capture the mean. So your confidence is lower. 90% confidence interval is narrower than a 95% confidence interval, which is narrower than a 99% confidence interval. Okay, and the numbers will bear that out also. 1.64, yep. Okay, and that's where we're not making these numbers up. That's where these numbers are coming from. So it's plus or minus 2.58 times the standard error, which is 3. So this time, what will we calculate this to be? Clear. K would be 3 times 2.58 equals 7.74. I'm going to store that here. Okay, and my mean was 150 minus, oh, no, I lost it. 3 times 2.58. Okay, put that into memory. Clear. 150 minus that standard, that margin of error is 142.26 to 150 plus oops. What does that equal to now? Memory recall. 157.74. Okay, I added the margin of error, added and subtracted the margin of error from our calculated mean from our sample. Not real hard, right? Okay, now now you guys get a chance to do the next one. I don't want to do that. A random sample of size 36. Only difference here is the sample size is different. Okay, has a mean of 150. Assuming the population normally distributed with standard deviation of 30, it's the same standard deviation. Only thing that's changed here is the sample size. Calculate the standard error for a sample size n equals 36. You guys work on it. You guys at home do the same thing. Okay. Oh, good thing you guys are working okay at home there.
Question, I'm sorry, question number 3.
Question number 3, yep. Calculate a standard error for sample size 36 from a sample where the mean was 130, but 150, but you know the population standard deviation is 30. So first thing you're going to do is calculate your standard error. Okay, sigma over the square root of n. Okay, anybody got a guess on it? Should be pretty easy, right? 5, right? Okay, yeah. It's 30 divided by the square root of 30, square root of 36, which is 6. 30 divided by 6 is 5. Compute a 95% confidence interval for the mean. Okay, how are you guys doing at home? Somebody at home want to type in the lower limit and the upper limit for the 95% confidence interval? I think yours is updating quicker than mine. Oh, there you go. Okay, I see him. Oh, excellent. Okay. Okay, so what do we get for a 95% confidence interval? Well, I know it's going to be roughly, I know just by looking that the standard error is 5, right? And I'm going to take 2 times the standard error roughly. So it's going to be 10. So it's going to be roughly 140 to 160. So what do the numbers actually come out to be?
I got 140.2.
140, okay, 0.2 to 159.8. Okay, excellent. How about the 99% confidence interval? Hey, Emily, are you working on it? I see you put up a number before that seemed okay. Right? Remember, we're going to calculate the standard error. Okay. You're going to calculate the standard error and you're going to add and subtract that. Ah, excellent. Good work. That's the lower range, right? Now find the upper limit. Right? Confidence interval has excellent upper limit and a lower limit and an upper limit. Okay, what do I got for the 99% confidence interval? Only difference, 2.58 times the standard error of what was it? 5? 5, right? Added and subtracted. Okay, excellent. Okay, and now here's a little twist, 90% confidence interval. You're not going to get answer 90% confidence interval too often, but it'll come up occasionally. Okay. And this is going to be the narrowest one because we're willing to accept more risk of the mean falling outside of the range, so we can afford for it to be narrower. It's also narrower simply because the number we're multiplying the standard error by is a smaller number, 1.64. So we're adding and subtracting a smaller number, which makes it a narrower range. But intuitively, you know it's going to be a narrower range only because you have less confidence that you're going to capture the mean. So that less confidence is because it's a narrower range. Okay, any result there? Online, guys online? 90% confidence interval. Remember, this time we're using a z-score of 1.64. Ah, excellent. Good. Excellent. Good work, Emily. You got the right answer. You just got not giving me the upper limit. Okay, remember, confidence interval is 2 numbers. It's a range, an interval. Okay, excellent. Ah, I see what it is. It's a coordination issue, not a math issue. Okay, let's take a look at number 4. Suppose we want to estimate the average weight of an adult male in DeKalb County, Georgia. We draw a random sample of 1,000 men from a population of 1 million men. Population, million people, we sampled 1,000. 1,000 a large sample? Okay, real large. Okay, and we weigh them. We find that the average man in our sample weighs 180 pounds. That's X bar, right? Not mu, but X bar. The sample is very large, so we're going to assume, for the purpose of analysis, that the standard deviation is the same as the population standard deviation, which is 30 pounds. The standard deviation of those 1,000 men is 30 pounds. We're going to assume that, since it's such a big sample, that the standard deviation, that sigma is, that 30 pounds approximate sigma well enough for us to use it for our confidence interval. What's the 95% confidence interval for the average weight of men in DeKalb County? Well, first thing I need is my confidence interval. I need my margin of error and my standard error. And see, I'm going to work with you on this one. Okay, X bar is equal to, what did I say? X bar, where is my, okay, that's already set. X bar was 180.
On my calculator, doesn't go there.
X bar and sigma is 30. And my sample size is 1,000. So my standard error is going to be equal to 30 divided by the square root of 1,000. Okay, I'm going to have to do a little bit of math here, right? This one I didn't give you such a nice, easy, round number. So 1,000, let's see, that's 1,000, square root of 1,000 is 31.62. So I'm going to store that in memory. So I'm going to get my 30, which is my standard deviation, divided by my square root of 1,000. And my standard error is going to be 0.9. I'm going to call it 0.95 for our purposes right now, is equal to 0.95. Okay, so a 95% confidence interval is going to be equal to X bar plus or minus 1.96 times my standard error. Okay, X bar is 180 plus or minus 1.96 times 0.95. Okay, this is going to come out to be my plus or minus, and let's calculate it, times. Now notice I mentioned this a few times. If you don't round this off and you keep all your decimal places, it's more accurate. Better to round off at the end. So I'm going to multiply by, I don't know if I hit times yet. Okay, times 1.96 is equal to 1.86. So it's 180 plus or minus 1.859 or 1.86. See, my error is smaller there if I don't round until after I complete that part of the analysis. So even adding, whenever you multiply or find roots or squares and stuff like that, you multiply the error. So roughly, for argument's sake, our confidence interval is going to be 181.86. Is going to be our upper limit. Our lower limit is going to be 178.14. Okay, 99% confidence interval. What's the only good thing that's going to change here for our 99% confidence interval is going to be our z-score. 180 plus or minus 2.58 times 0.95, right? And that's for our 99% confidence interval. Let's calculate that. 180, whoops, let me clear all this. 2.58.
Which one works out the number?
I'm sorry.
So 99%.
Okay, I'm sticking with it down. I'm doing 1 and 3 first.
Okay. That's
Okay, it's because I'm since I'm working with the standard error for those two. Okay, so 99%, 180 plus or minus 2.58 times that, and let me get my calculator back, equals 2.58 times 0.95 equals, whoops, 2.58 times 0.95 equals, calculators on computers are like really, they've never been really very useful, right? So very convenient. I'm going to store that in memory. Okay, and I'm going to let's see, that's going to be my, that's going to be my margin of error. So it's going to be equal to 180 plus that, which is going to be 182.245. And our lower limit is going to be 180 minus 2.45, which is 177.56. Okay, now the same population, right? For the same population, let's assume that our sample size is 100 instead of 1,000, right? If the sample size is 100 instead of 1,000, it's going to change my standard error. right? It's going to change what the standard error is because the sample size is different, right? But it's exactly the same population. So I'm going to calculate a 95% confidence interval and a 99% confidence interval again for the same problem. Now, our sample size is still big enough for us to assume that the standard deviation of the sample is the same as the population, okay, for us to take that liberty. Okay, if it's less than 30, then we can't do that anymore. We have to make a correction for that, and we'll be learning about that next week. Okay, so let's do this now. Okay, so somebody want to tell me what the result here was? It was 180. What was the 95% confidence interval? What was it? The range. What was it? I don't remember. I didn't write it down.
Oh, for number 2?
For number 1 and number 3.
Did you put,
Number 1 was 178.14
1.4?
to 181.86.
Okay, and the 99% confidence interval?
177.55 to 182.45.
Okay, good. So now I'm going to repeat this for sample size of 100. For sample size of 100, my standard error is going to be equal to 30 over the square root of 100. Right? This time my standard error is going to be equal to 3. So for 95% confidence interval, it's going to be x bar plus or minus 1.96 times my standard error, which is 3. Okay, so now this is going to be 180 plus or minus 1.96 times 3 is going to be 3.
2.58?
I'm sorry?
If the 99%, is it going to be 2.58 times 3?
Oh, I'm doing 95%
Oh,
first.
I'm sorry.
Okay. Okay, plus or minus 4. What is that? 3.92. Am I right on that? No, I'm sorry. 3.5. 5.88. You're right. Yep, you're right. 5.88. Okay, so that's going to be, my range is going to be, my upper limit's going to be 185.88. And my lower limit's going to be what?
174.12.
Okay, let's compare the two of them. Okay, now for the same confidence interval, 95% confidence interval, we had a big sample size, 178 to 182, right? Roughly 178 to 182. For the same population, for the same standard deviation, and so on and so forth, different standard error, now it's 174 to 185. Our confidence interval got wider because it's a smaller sample size. Makes standard error a bigger number, makes the margin of error a bigger number, so it's going to be a wider range. Right? So all these things kind of make sense when you kind of look at them. The cause and effect really intuitively make the same sense as the math does. Okay, and for 99% confidence interval, we're going to do the same thing. 180 plus or minus 2.58 times 3, and 180 plus or minus, okay. Let's see what that's going to be. 2.58. Clear. Up. Times 3. And I'm going to store this in memory. So 180 minus, it's going to be 172.26. And the upper range is going to be 187.26. I'm sorry, no, 174. Okay. All right, guys, is that okay? Anybody have questions on that? Simple